Okay, so the last like geometric application we're going to do for this chapter is looking at the arc length of a curve, and then um, if we revolved the arc length around, what that would look like. So we're going to start with the proof. So I have to find the arc length. If I want to find the arc length between these 2 points, x sub naught and y sub naught, and x sub 1 and y sub 1, basically what we're going to start out with is the distance formula so that I can figure out, the straight distance between these 2 points. And then we'll apply some of our calculus. So here we go. So the distance formula is equal to the square root of the change in x squared plus the change in y squared. What I'm going to do next is multiply, oops, that's not a highlighter, multiply by a form of 1. Which I put in as the change in x over the change in x squared. Then I'm going to separate those equations, and I'm going to pull this 1 over the change in x squared in with the change in y squared. Okay, so you can see that happens here. Then I'm going to, because I did that, I now have common factors of change in x squared. So I'm going to factor out the change in x. Then I'm going to, because I factored out the change in x squared, I can actually take the square root of that. So that gives me the change in x times the square root of 1 plus the change in y over the change in x squared. And then, so I just did the square root of the change of x squared is equal to the change of x. Then I'm going to take the change in y over the change in x and squared, and I'm going to say, hey, remember the change in y over the change in x? That is the slope, or f prime of x. Okay. Finally, I'm going to cut up delta x into infinitely small pieces and add them up, which is just an integral. So if delta x is infinitely small, I think about this as rendering, when on the computer, when you just keep having your sections in half and half and half until they're infinitely small, we get a smooth curve. So that's basically what we're doing here, but calculus. Integral to add up. Okay, so basically what we end up with in the end is that the arc length of a curve is equal to the integral from a to b, the square root of 1 plus f prime of x squared dx. Okay, so remember the integral adds up all the pieces, the dx cuts everything into infinitely small pieces. So it's our rendering. So we're going to find the arc length between f of x is equal to x squared on the interval from -1 to 1. So all I need are the bounds, and I need my derivative of the curve. So if I were to just graph this really quick, x squared, 1, -1, 0, 1, looks like this. So we're going to find the arc length between -1 to 1. So I need the derivative of f of x, so that's 2x. Now I can find the length, which is the integral from a to b, so from x is equal to -1 to 1, of the square root of 1 plus the change in y over the change, the change in y over the change of x, which is just the derivative, so 2x squared dx. And then I substitute that into my calculator to give me a length of 2.598. That's it, y'all. You need the derivative and some bounds. Okay, let's do another one. I have the arc length of, we're going to find the arc length of y is equal to 3 over 2x to the 2/3 on the interval from 1 to 8. So I can already see my interval, my bounds are a to b is 1 and 8. I'm going to take my y prime, because I know I'm going to need that later. So 3/2 times 2/3 is 1. Then I have x, decrease the degree by 1, so to the negative 1/3. Now we can find our arc length is the integral from 1 to 8 of the square root of 1 plus x to the negative 1/3 squared dx. All right, calculator, 8.352. The arc length is equal to 8.352. All right, that's arc length. Now we're going to do the surface area of a revolution. Okay, so we can basically take the idea of volume by rotation and arc length to find the surface area of a solid. Okay, so that's like the outside or the peel of your object. What we're going to end up doing is taking this little curve here. So I want to take the arc length between A and B, and then I'm going to rotate it around the x-axis, have a horizontal axis. So it's going to create like a circle like this, right? Around, just like different size circles. So the height between the curve, the x-axis and the curve is going to represent, I'm going to take these things away, is going to represent r, and that is just going to be like top curve minus bottom curve, okay? And then because we're wrapping, this is like really similar to like shell method. What we're doing is taking the circumference of the circle and multiplying it by the arc length, basically. So the 2 pi r is the circumference, and then the root 1 plus the f prime of x squared is the arc length of the circle, of all the different of the circles. No, sorry, the arc length of the curve, okay? And then you rotate it around and it makes a circle. This is like the toilet paper roll all over again. Okay, so the same thing is going to happen with a vertical line of rotation, so around the y-axis. So this time I'm going to take this curve right here, and I'm going to rotate it around my axis of rotation. And so I'm going to unpeel this little part of the curve, and I end up with the circumference is 2 pi times the radius, which in this case, the distance from the curve to the axis of rotation is r, and then you're just going to multiply that by the arc length. Okay, so the area, we're going to find the area of the surface of revolution formed by revolving the graph of f of x is equal to x cubed on the interval from 0 to 1 about the x-axis. So the things that I need are the derivative. So f prime of x is equal to, and well, f of x is equal to x cubed. So the derivative would be 3x squared. And then it says my bounds are from 0 to 1. So a is 0 and b is 1. And finally, we need the r value. So if I have, we're going x cubed from 0 to 1. So from 0 to 1, the curve is concave up like that. And we want to revolve that around x-axis. So I'm going to take this point and I'm going to revolve it around the x-axis. So the height is going to be, so the distance from the curve to the x-axis is going to be my r. So that would just be the top curve minus the bottom curve, which in this case is x cubed minus 0. Okay, so r is equal to x cubed minus 0. So now we can just plug this into our formula. So the surface area is equal to 2 pi times the integral from a to b of r times the square root of 1 minus f prime of x squared dx. So the surface area is equal to 2 pi times the integral from 0 to 1 of x cubed times the square root of 1 minus 3x squared dx. So again, I use my calculator here. The surface area is equal to 3.563. All right, so we're going to find the last one. We're going to find the surface area formed by revolving the graph of x squared around on the interval 0 to root 2 about the y-axis. So I like to sketch these. So from 0 to square root 2. So I know at 0, 0 for x squared, 0 is equal to 0. And then at root 2, the y value is going to be root 2 squared, which is just 2. So 1, 2. Okay. So then I'm going to find the surface area of this curve rotated around the y-axis. So I'm going to take this curve and I need to rotate it around the y-axis. So that means that the radius is the right curve minus the left curve. So r is equal to, and the problem here is that we're written in terms of x, so I need to write my curve in terms of y. So x is equal to the square root of y. So I'm going to have the square root of y minus 0. Okay, lastly, I'm going to go ahead and, well, it's not last, but we're going to do 2 pi times the integral. And because we're cutting in terms of dy, I need the bound, my bounds are from 0 to 2. So 0 to y is equal to 2. My radius is the square root of y. And then I need to multiply by the surface area. So the square root of 1 minus f prime. But guess what? We're written in terms of y. So I need to say that x is equal to y to the 1/2 power. Take the derivative of both sides. So x prime is equal to 1/2 y to the negative 1/2 power. So now I'm going to substitute that into my surface area equation. So plus 1/2 y to the negative 1/2 squared. And then I use my calculator. So the surface area is equal to 13.614. Yay! That's it.